Saxon Algebra 2, Lesson 59. It's a three-parter, you guys. Bear with me. It's going to be fun, though, because in the first one, we get to pretend we're scientists. All right? Scientists do a lot of experiments. That's a quality definition of what scientists are. They do a lot of experiments, and they tend to do the same experiment over and over and over because they're trying to make sure that whatever theories they're developing or hypotheses they're testing, that their results are consistent and reproducible, right? That's the whole thing about science, is it has to be reproducible so that we know it's true and not just one guy's experience or woman's. So what scientists do is they run a bunch of experiments and then they graph their results on the same graph so they can see if there's a trend or a pattern. This is an approximation of a scientist's notebook. This scientist has done some sort of study that involves taking copper and then doing something to it and getting bronze as a result. And they're measuring how much copper they start with and then how much bronze they end up with. And so they have created ordered pairs of copper they had in the beginning, bronze they had in the end, and then they've graphed those points. And they're big and circular like that. That's John's way of reminding you that they are experimental data. They're not as valid as a lot of the points, that they're not as exact and precise as the points we usually work with as mathematicians. Because they're scientific experimental data, they're a little bit fuzzy. So what scientists have to do, is they're trying to see if this data will approximate a line, right? Because if it's a line, then they can write the equation of that line, and that line will have important scientific significance because it will say, if you take this amount of copper, you will get that amount of bronze, and it's a predictor. So scientists are into that idea of using experiments to develop lines that they can write the equation of. Now, all of this can be done by computer, and actually quite simple graphing calculators can do this. So no one's running around doing hand calculations of this anymore, but we're going to, because we want to just learn how the numbers work. And the good news is you already know how to do this, because you know how to take 2 points and find the slope and then find the y-intercept. We've been doing that for quite some time. So the only thing we're going to do is just pretend to be scientists as we do it. And that's fun. You get to put on an imaginary lab coat, maybe some safety goggles if you're into it. I personally would like to have my name. I think I would like to have Dr. Stryker in blue script above the pocket of my lab coat. And, we'll probably have to do a special hand wash before we enter the lab area. But this is what we're doing. So the only part of this that is hard is that we have to find 2 places on this line or on this graph rather, where the line goes exactly through the corner of the points so that we can read the values really easily. So for example, this right here where the line crosses the graph paper, if you will, that's a terrible choice because it's in the middle between, let's see what it's between. It's between 15 and 17 and a half, right? Because this is going up by 2.5 each time. This is terrible. I don't know what that point is. That's too vague. I want to find a place where the line goes right through the graph paper. This one looks a lot better. I'm going to use that as one of my points. And that will be 15, 40. Okay, so I'm going to write that down. $59.1, and what did I say? 15 and 40. That's going to be one of our points. Now, notice that the scale of the graph on this side is different than the scale of the graph on this side. This one's going up by 5 each time, and this one's going up less. It's going up by 2.5 each time. That's okay. Don't worry about it. That doesn't matter. As long as we choose our numbers and work accurately, we'll be fine. This is the other point that looks decent to me, and that would be 5, and let's see, it would be 5 over here, right? So it's 5 and 5. You guys, this is the hardest part of these problems, is finding 2 points to work with that are clear on the line. Later, we're going to get to draw our own lines, and that will be much easier. Right now, we're stuck with the lines as John's drawn them, and sometimes they're really hard to read. So here's what you can do. If you need to get the original 2 points and you're just having a tough time finding 2 on the graph that look like the line is crossing right on the graph paper corners, look in the solutions manual and find out what points John uses. Then it's gravy after that. Super easy, okay? So now all we have to do is step 1. Now all we have to do is the actual problem. 1, find the slope, which we call m. Remember, this is y equals mx plus b. That is not only a mathematical equation, but for scientists, that's a model that shows how their 2 elements behave in relation to each other. So it's really important to get our data into this shape. Okay, the way that we find m is we use the slope formula. y2 minus y1 over x2 minus x1. Okay, so now all we have to do, I don't know why I did the parentheses that way, it wasn't necessary. Okay, use your buckets just to be sure. Let's call this x1 and y1, x2 and y2. Ready? y2 is 5, y1 is 40, 5, 15. Remember that it doesn't matter which pair of points you call the 1 points and the 2 points, as long as they're consistent and you call the right points x and y, you're good. 5 minus, I'll write it over here, it's minus 35 over minus 10, right? So that equals, we can change it to 35 over 10. Now, my gut instinct is I want to leave this as a fraction form. I want to divide top and bottom by 5 and get 7 over 2. But here's the thing. Scientists, which today we're pretending to be, don't like fractions as much as mathematicians do. They prefer decimals. So when I see this just begging to be a decimal, fine. We'll let it be a decimal. Our slope is 3.5. Okay? So lean into the decimals on these problems, whatever, right? Okay, now we're going to use this. We're going to use this for m. We're going to use this for our x values, just like we've done before. So we're going to say 5 equals 3.5 times 5 plus b, right? We're just plugging in what we know. I chose what I thought was the easier looking pair of points, but you could have used the 15 and 40 as well. Okay, 3.5 times 5. Let's do that one. That's 25, 2, 17, 1 decimal place. So this is 17.5. I'm going to subtract 17.5 from both sides. This is all the same as we've done before. That's all gone. This becomes what? Minus 12.5 equals b. Okay, so now we know what to do. We just write it in that form. We write y equals, where's my m? There's my m. 3.5 x minus 12.5. That looks really good, right? But there's only one more thing we want to do that is just window dressing. What we want to do is, instead of calling this one x and this one y, we want to relate this line more to our experiment. So we, instead of writing x, we find out what this element is, copper, and we see, oh, let's use Cu as that abbreviation. And does it say it up here? No, it doesn't. If you don't know this, we could just use C, and then we'll put B for Y in. So what we'll do is we'll just rewrite this as B equals 3.5 C. I'm going to pretend I don't know the abbreviation for copper, minus 12.5. Okay? So that just makes us feel sciencey. And again, we just put in the letter that matches to the x-axis where the x goes, and we put in the letter that matches to the y-axis where the y goes. And we're done. Yay. One more of these. Again, they're not difficult once you get your points chosen. And so let's see. This one looks good. This is, you have to be careful reading the graph because there are so many different scales. 10, and let's see, this is going up by, it would be 1. So I'll have 10 and 1 And then that one looks pretty good. Right there, that looks pretty good. So that would be 15 and 2. Okay, so I'm going to use those. I don't know if that's exactly going to work out with John, because if I chose values where the line isn't precisely on the corner, that could mess up the calculation. But I'm going to show, if that is what happens, then I'll show you how it works if you're off by a little bit. x1, y1, x2, y2, m equals, I've got all my equations up here, so I'm not going to write them again. Right, I'm following this same pattern, so I'm going to go 2 minus 1 over 15 minus 10. Okay, so that will be 1 over 5. Which looks pretty good. And then I'm going to write this as a decimal. So I'm going to bump that up to 2 over 10, and that will be 0.2. Make sense? Okay, so there's our value for m, and now I just plug in, which pair of points should I choose? I'm choosing the 10 and the 1. 1 equals 0.2 times 1 plus b. This is minus 0.2, right? Because 0.2 times 1 is 0.2. So I subtract 0.2 from both sides, and I get 0.8 equals b. And then I know I'm going to write it in this format, but I want to find the fancy letters instead of the x and the y. We have sulfur and nitrogen. So I'm just going to put S and N. N is the one on the y-axis. N equals 0.2 times S plus 0.8. So that is my answer. Okay? Now, and again, you don't really have to understand anything about these. Just pick the letter that matches to the x-axis. Pick the one on the y-axis. There's no science involved, even though we're faking it, right? Now, look what happened here. This answer that John has here, you can't see it. This answer that John has, he got 0.18 for the slope. He got the same as me. Oh no, he got negative 0.8, and this is positive. Now, my answer is still valid because he just used different points. And as a scientist, that's okay. As a mathematician, this is an incredibly frustrating kind of problem because our answers don't always come out the same. So what I do is I compare. He got 0.18. Well, that's only 2/100ths different than mine, right? Because mine's 0.20. So it's just 2/100ths different. But that 2/100ths is enough to change that from that. I accept this as the answer because my points are different. And that's what is frustrating in these. And you're going to want to rip your hair out. So that's what, well, that's violent imagery. So what I suggest you do is like when I picked my points right here, 10 and 1, 15 and 2. He shows it differently here. In the solutions manual, it will show it differently. If I look at this diagram carefully, I can see, oh, John chose, wait, what did he choose? He chose this? Yeah, I don't like his way of doing it at all. My answer is better. Boo-hoo. Go away, John. Sorry, that was mean. You know I love you, John. That's the frustration in these, is that as mathematicians, this is a relatively imprecise process, and it is very frustrating. The good news is that in real life, even in science classes, you're not going to make these calculations by hand. What you're going to do is you're going to use a graphing calculator, and you're going to plug in all of these pairs of your experimental results, and then the calculator will give you the equation of the line. All right? So we're just practicing. Don't let these problems make you crazy. Now, let's try something else to frustrate us, shall we? This one won't be bad. decimals and fractions. We just have one of these problems. So let me write it down and you'll immediately see the drama. It's 59.3. You're copying, right? I'll give you a second to catch up. All right, this is a system of equations that we're supposed to solve, just like any other system of equations, substitution, elimination, whatever we want. But the problem is that we have decimals and fractions lurking in our numbers, thus the title. No, 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 we're not going to do that. I refuse, on principle, to deal with those fractions, and I refuse to deal with those decimals. So what we're going to do is we're going to learn some techniques to blow them up right away. To blow these up, to blow up fractions, we use a least common multiple. We multiply everything by the least common multiple. So we can quickly calculate it. 2, 5, and 5. Okay, that would be 10. We multiply everything by the LCM. And then we can cancel, right? So 10 against 2, I'm going to have 5. 10 against 5, I'm going to have 2. And I'm going to put parentheses around to show that I need to multiply that. And then 10 against 5 is another 2, and they're my parentheses. This one was just an x, so it was fine. So I'm going to rewrite that top equation as 5x plus 6y equals minus 4. Oh, Lord have mercy, so much better, right? And now, our second step, to blow up decimals, we're going to jump the decimals. Now, what we have to do is we have to figure out which one of these is giving us the biggest drama. This has 2 decimal places. This only has 1. This has 2. We have to jump by the same number of jumps on each term. And so we want to pick the highest number of jumps we need so that every number is drama-free in the end. That means we have to be careful with these guys. So we're going to move it twice. Twice. Ooh, that means we're going to have to squeeze another 0 in there. And then twice. So this becomes 6x minus 20y equals 104. Oh. Don't you think that is so much better? I feel much better about it, okay? So now we're just down to a basic problem. Let's use elimination. Let's eliminate the x terms, just because their numbers are a little lower. So I'm going to multiply this one by what? 6, and this one by minus 5. That will make me happy. Okay, so let's multiply through. 6 times 5x. Did you get the same as me? Check and see. Okay, now I'm going to multiply the bottom line. Yes, okay, just a second. I'm checking my number against the answer. I'm looking in the book, and John just put his minus sign in the other place, so it freaked me out for a minute. Now we will add, and we will get 136y equals minus 544, which means we're going to have to divide by 136. And I'm guessing that 136 goes into that, what do you want to say, 4 times maybe? Let's try it. 136 times 4. Yes. 136 times 4 is 544. So y equals minus 4. Oh, that's nice, right? Then we have to plug it into one of these. I sure am not going to plug it into one of those. Let's plug it into one of these. Maybe this top one is a little bit easier to work with. So we'll say 5x plus 6 times minus 4 equals minus 4. This is minus 24, so we're going to have to add 24 to both sides. 5x equals 20. And that means that x equals 4. So my final answer is 4 minus 4. Okay, so once we took care of this drama, then it was just typical. And so these are our two rules. To blow up the fractions, we multiply by the LCM. And to blow up the decimals, we jump the decimal, the number of times to clean it up in everybody. All right, you thought that like you'd survive this lesson? Oh no, there's another part. I consider this is probably against the, what are the rules about being kind to prisoners? You know, the Geneva Conventions, that's what I'm talking about. We have practiced going from rectangular coordinates. No. Yes, we've gone from polar to rectangular. Now we're going to learn how to go from rectangular to polar form. All right, it's not too bad. I say at like minute 45 of the lesson. 59.4. Convert minus 5r minus 3u to polar. That seems really hard, but let's just draw the picture. I can see right away this is going to be in the third quadrant, isn't it? Because it's both negatives. So I'm going to make that, I'm going to like zoom in. Okay, so we're going to have a point. It's going to be minus 5 on this side. And then it's going to be minus 3 on this side. So I'm just kind of eyeballing, right? I want this side to be a little longer than this side, but it doesn't have to be precise. Then that's where the point goes, right? Then I draw it, and because I want to turn it into a polar coordinate. So I draw a triangle that goes always to the x-axis, the right axis, if you will. We always draw our triangles back to this guy, never to this guy. That messed me up for a while when I was in high school. Okay, now this minus 3 we recognize, oh, that's also this length, right? So we know, if this is our angle, we know that this is the adjacent and this is the opposite. Okay, that's useful. Now, to create polar coordinates, what we need, I'm drawing my answer box. We're going to need the hypotenuse, and then we're going to need the size of, not this angle, but we're going to need that whole angle, aren't we? Okay, so how are we going to find either of those? Let's start with the angle, because we're used to approaching that first. If I use these two, okay, let's look at tangent, because that will relate. Tangent is over Arthur, right? So if I call this theta, then I can say that the tangent of that angle, theta, has to equal minus 3 over minus 5. Ooh, that's kind of cool, isn't it? And if I simplify this, it's 0.6. It'll become positive, right? So what I can do is put my calculator in second mode. Then I can enter 0.6, and then I can hit, remember this means inverse tangent, and that is the button I use when I have the decimal and I want the degrees, which is exactly our scenario. We have the decimal, we want to convert that into the degrees using tangent, and what we will get is that angle is 31 degrees. Okay, we'll get theta equals 31. I think it comes out to 31.0. Okay, now here's the tricky thing. That is not the number we write here, because this number represents this much of the angle, but the number that goes in here has to be all of that. So we have to stop and use our brains for a second and figure out, okay, we know that much is 31, but how do we figure that? Oh, we add it. We need to take the 31 and we need to add 180, right? Because we need it to be this 180 plus the 31. So that gives us 211 degrees. That's what goes here. Oh, isn't that so nice? I'm happy with that. All right. Now, there are a couple ways that we can come up with the hypotenuse, and I'm going to show you the way that I prefer, and then in the future I'll show you a different way, and you can add that to your bag of tricks if you want. Now we know the size of this angle, so I can use, let's write down sine and cosine, right? Oscar had a hold. I've got the adjacent, I've got the opposite, I've got the angle, right, the theta that goes there. It's 31 degrees just to do the trig on this little triangle. I could use either of these with either of these to calculate the hypotenuse. So I'm going to choose sine. So I know that the sine of this angle, which is 31 degrees, has to equal the opposite, minus 3, over the hypotenuse. Huh. Pretty cool, right? I can also ignore the fact that this is a negative. That's not really important because the hypotenuse is always positive. We don't have to worry about the negative sign. I can just take the length of it, right? So I don't need the negatives, and I really didn't even need them here. Okay? We're just, the length of this side is positive 5. The length of this side is positive 3. We use these minus signs to get us in the third quadrant, but when we're just looking at this triangle, those negatives are no longer important to us. Okay, so now what I'm going to do is I'm going to cross multiply and flip those two, and I'm going to get that the hypotenuse will equal 3 over the sine of 31 degrees. I can now grab my calculator. I'm going to do 3 divided by parenthesis 31 sine end parenthesis equals. Whew. See if you can get that to work out. The right answer is 5.83. And remember here, we're not using the second. We're not using the inverse trig function. This is just the regular trig function. Okay? Because in this case, we have the degrees and we want the decimal. So that's what we use the basic button for. Okay? So our hypotenuse is 5.83, and that looks kind of logical given those values. That number goes here, and that's our final answer. Yay! We're going to practice a lot more of those. Honestly, you guys, those problems we started with, those annoying scientist ones where we have to play around with those weird values and we can't read the chart very well, those are annoying and frustrating. This is super important. I wish this would have been first and those problems would have been last. Oh well, John didn't ask me. All right, that's all of lesson 59. Lesson 60, you guys, is going to be way more direct and to the point. Sorry for all this drama. Bye.